everybody. We're getting ready to do pre-calculus math lesson 4.1 part 2. Okay, so today's bell work, teachers. Sketch this graph here, students. This is a cube graph here. And the graph of the function of g. So we have g of x, and then we have our parent function here. F of x equals x cubed. That's your parent, and then this is your derivation from your parent. So describe transformation. Describe your transformation here in these response boxes, students. And teachers, give your students about 6-7 minutes for this. Okay, welcome back everybody, and let's find our solutions now for our bell work today. For 123, we have this situation here, cubed, and how that relates to f of x equals x cubed. Here is f of x equals x cubed. Here we have a shift to the right 1 unit because of your -1 here. That will be your graph there. This will be an acceptable explanation for that. And then for 124, the graph of g is a vertical shift 4 units downward of f of x equals x cubed. And this would be your shift here from up here, your parent function there. Page 1 of our classwork, we go right into example 3, converting from radians to degrees. So -pi/2 radians equals how many degrees? So we use our conversion factor here. We multiply -pi/2 radians times 180 degrees over pi radians, and we get -90 degrees. So we multiply by 180 over pi. And then up here for 2 radians equals 2 radians times our conversion factor equals 360 over pi, or 114.59 degrees. Again, multiply by 180 over pi. And then see here, 9pi/2 radians. How many degrees does that equal? Again, multiply by our conversion factor, and we get 810 degrees here, multiplied by our conversion factor. Let's go into an example here, converting from radians to degrees. Rewrite each angle in degree measure. So I'm going to write this in degree measure, and this, well, this is on you, students. I'll do this one in class, and then this is you in class. So up here, 3pi/2 times our conversion factor will give us 270 degrees here. Two positive angles, A and beta, are complementary, complements of each other, when their sum is 90 degrees, or pi/2. Two positive angles are supplementary, supplements of each other, when their sum is 180 degrees, or pi. So here's an example here of complementary angles. Alpha and beta here are complementary, and then alpha and beta here would be supplementary here for the straight angle. Let's go into another example here, example 4, complementary and supplementary angles. If possible, find a complement and supplement of each angle. So we have 72 degrees there. So the complement of 72 would be found by subtracting 72 from 90, which would be 18 degrees. The supplement is 18 degrees here. And then the supplement for this angle will be 180 minus 72 would equal 108 degrees. So your complement is 18, your supplement would be 108. And then for B here, 148. So because 148 is greater than 90, there is no complement. But for the supplement, you would subtract 148 from 180, and you would get 32 degrees as your supplement. And then for 2pi/5, the complement is pi/2 minus 2pi/5 would equal 5pi/10 minus 4pi/10 would equal pi/10. So pi/10 would be your complement. And then the supplement is pi minus 2 pi over 5. We do our arithmetic here and we get 3 pi over 5 would be our supplement radian measure for 2 pi over 5. And then 4 pi over 5, because 4 pi over 5 is greater than pi over 2, there is no complement. Now for the supplement, you would go pi minus 4 pi over 5, and we convert these over to our least common denominator here, and we would get pi over 5 as our supplement for that. Okay, into our guided practice. In these exercises here, find, if possible, the complement and the supplement of the angle. We got a 24-degree angle here, and then we got 129 down there for you students. So up here for 24 degrees, our complement will be found by subtracting 24 from 90, and then our supplement will be subtracting 24 from 180. Here's your complement, and then here's your supplement. This is for you students down here. Linear and angular speed. The radian measure formula, theta equals s over r, can be used to measure arc length along a circle. So arc length for a circle of radius r is central angle theta intercepts an arc of length s given by s equals r times theta. Length of a circular arc. Here is your formula for the length of a circular arc, where theta is measured in radians, so this would be radians here. Note that if r equals 1, then s would equal theta, and the radian measure of theta equals the arc length, so that will be how you find your arc length. Let's do an example from that. Finding an arc length, a circle has a radius of 4 inches. Find the length of the arc intercepted by a central angle of 240 as shown. So we have a central angle here of 240 degrees. Here's your central angle, theta, and then here is our arc out here, s, and then r equals 4. So, okay, to use the formula s equals r theta, first convert 240 to radian measure. So what would 240 be in radian measure? Well, we need our conversion factor here. Pi radians over 180 degrees. So we multiply 240 by this and we get 4 pi over 3 radians here for our central angle here. So then using a radius of r equals 4, here's our radius here, you can find the arc length to be 4 times 4 pi over 3, which equals 16 pi over 3, and then when you do your arithmetic, you get 16.76 inches for s out here. Note that the units of r theta are determined by the units of r because theta is given in radian measure and therefore it has no units. It's kind of a universal measure. Okay, let's get into our guided practice here. Find the length of the arc on a circle radius r intercepted by central angle theta. So we got a radius of 14 and then a central angle 180. And then down here we got a radius of 9 and then a central angle of 60. Students, that is your independent practice there. We're going to do our guided practice now in class. S equals r theta, theta in radians. So what we need is to put this in radians. So S equals 14 times 180. 180 would be our radians equals pi over 180, which equals 14 pi, which equals 43.982 inches for this one here. S equals radians times theta, and theta would be in radians. We're going to convert 180 into radians here. Here's our conversion factor. These will cancel, so it'll be 14 pi radians times, we multiplied it by 180 and we get 14 pi is 43.982 inches for this situation here. Okay, the formula for the length of a circular arc can be used to analyze the motion of a particle moving at a constant speed along a circular path. Now, linear and angular speed. Consider a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time t, then the linear speed of the particle equals this. Linear speed equals arc length over time, and it's symbolized by s over t here. Moreover, if theta is the angle in radian measure corresponding to the arc length s, then the angular speed of the particle is central angle over time, or which equals theta over t. Linear speed measures how fast the particle moves, and the angular speed measures how fast the angle changes. So we have angular speed, and then we have we have arc length as well to figure. But now we can figure angular speed because we know our central angle over time as well. So angular speed. Finding linear speed. The second hand of a clock is 10.2 meters long. Here's our second hand here, 10.2. Find the linear speed of the tip of this second hand. Well, to do that, the arc length that traveled is s equals 2 pi r. 2 pi r is our this is the formula here for the circumference of a circle. So 2 pi 10.2, here's our r here. We multiply that together and we get 20.4 pi centimeters here as our circumference. The time required for a second hand to travel this distance is 1 minute. So now the linear speed of the tip of the second hand is linear speed equals s over t, and our s here is 20.4 pi centimeters over 60 seconds. So for that, it'd be approximately 1.07 centimeters per second would be our angular speed. Okay, now our guided practice here, 108. Mechanical engineering, students. The circular blade on a saw has a diameter of 7.25 inches and rotates at 4,800 revolutions per minute. Find the angular speed of the blade in radians per second here. We're going to do that in class. And then yours down here, student, independent practice. Find the linear speed of the saw teeth in feet per second as they contact the wood being cut. So find the linear speed as well as find the angular speed of this situation here. So to do that, to find our angular speed, we have to use our formula here. Revolutions per second equals 4,800 over 60, which equals 80 revolutions per second. 4,800 divided by 60 is 80 revolutions per second. So our angular speed now, we multiply 2 pi times 80 equals 160 pi radians per second. And then down here, students, this one's on you. Let's go into another example here, example 7. Finding angular and linear speed. A 15-inch diameter tire, this tire here is 15 inches in diameter, on a car makes 9.3 revolutions per second. Find the angular speed of the tire in radians per second. So we need to find the angular speed of the tire in radians when we know it's 15-inch diameter and 9.3 revolutions per second. So because each revolution generates 2 pi radians, it follows that the tire turns 9.3 revolutions times 2 pi equals 18.6 pi radians per second. We know we can get that much from what we're given up here. In other words, the angular speed is theta over time, and then theta in this case is 18.6 pi over per second here, 18.6 second. So now 18.6 pi radians per second. Find the linear speed. Now that we know our angular speed, the linear speed of the tire and car is linear speed equals s over t. So we have this here, which is our s. R times theta over t. So our radian here is 1/2 of 15, which will give us a radius here is 15-inch diameter. So a radius will be 1/2 times 15 times our radian here over 1 second. And when we crunch that on your calculator, you get 438.25 inches per second. Okay, into our guided practice. A computerized spin balance machine rotates a 25-inch diameter tire at 480 revolutions per minute. Find the road speed in miles per hour at which the tire is being balanced. So this is what we're going to do in class. Students, this is what you are responsible for down here. So to do this problem here of angular speed, we have an angular speed of which we need to figure out here with a 25-inch diameter tire that we know goes at 480 revolutions per minute. So we need to find the road speed at which the tire is being balanced. So we have a 25-inch tire going 480 revolutions per minute. So we need to convert it into per hour, revolutions per hour. So we got 480 over 1 over 60, which comes out to 28,000 revolutions per hour. So to find angular speed, we multiply our revolutions per hour times 2 pi, and that'll give us 57,600 pi radians per hour. And then the radius of the wheel is 25 over 2. And then we got to find how many revolutions of the wheel it takes to go for 5 miles here, I guess is what we're figuring here. So 25 over 2 divided by 12 inches per foot, 5280 feet per mile. So for every 25,344 revolutions, we go 5 miles. So now that we know for 5 miles is 25,344 revolutions times 57,600 radians, and when we do this multiplication here, we get 125 radians over 11, which comes out to 35.70 miles per hour when you are rotating this wheel at this speed here. Per hour, it would be equal to 35.70 miles per hour. And that's your 4.1 lesson of pre-calculus math. Any questions, email me here for note-taking guides, and solution PowerPoints, etc. Email me here. Thank you very much.